Welcome to part 2 of this week's online lecture. In part 2 we will use the information about moments of inertia and reduced mass to discuss the results from the Schrödinger equation we get for the rigid diatomic molecule. In order to set up the Schrödinger equation, we need to know what the Hamiltonian is for my rotating system. And it looks like this. Note that the mass that appeared in the Hamiltonian for the particle in the box has been substituted with the moment of inertia. And the del squared term is the second order differential operator commonly referred to as the Laplacian. Using this Hamiltonian and solving the Schrödinger equation will mean that the wave functions will be the rotational wave functions and the energies will be the energies of these rotational states. The form of the Laplacian depends on the coordinate system. For our rigid diatomic system, we employed a mathematical transformation so that we could express the system as the reduced mass rotating one bond length away from the origin. We can think of our system as a particle whose mass is the reduced mass moving on the surface of a sphere with a radius equal to the bond length. Well, if this particle is moving on the surface of the sphere, we need two spherical coordinates to describe its position. For example, latitude and longitude. The two coordinates are labelled theta and phi. So the Laplacian is the term in brackets. Admittedly, this equation looks complicated. But in fact you know the solution to this equation. Can you think of a situation in which you have a particle moving around an origin in chemistry? The classic example is an electron moving around a hydrogen nucleus in a hydrogen atom. What are the solutions for a hydrogen atom? What are the wave functions? The solutions are the atomic orbitals. The atomic orbital is the product of two components, a radial component and an angular component. Well, in our rigid diatomic, the radius is fixed, so there is no radial component. So the angular components for the atomic orbitals are the solutions to this equation. Technically, they're known as spherical harmonics. Note again that this equation is very similar to the equation we would have for linear motion. If it were linear motion, it would have been minus h bar squared upon 2m. All I have done to convert it from linear motion to rotational motion is to swap mass m for I moment of inertia. If we solve this equation, we have to take into account the boundary conditions, which mean we're going to get a quantized system. But why do we have boundary conditions? Well, remember that a wave function must be single valued. Imagine my particle moving around the equator on the sphere. The wave function will be changing as I go round the equator, but when it gets back to its original position, the wave function has to be the same as it was 360 degrees earlier. So that is the boundary condition. The fact that this boundary condition exists means I'm going to get quantization in this system, just like we had for particle in the box. And the solution leads to these quantized rotational energy levels. J here is my rotational quantum number, just like n was the quantum number in the particle in the box system. Please note that you do not need to know exactly how solving the Schrödinger equation leads to these rotational energies. All you need to know is that there are boundary conditions, and so we have quantization. The units of energy for this expression are joules. The J quantum number can have values of 0, 1, 2, 3, etc. So 0 and all positive integers. When J is equal to 0, our expression for the rotational energy tells us that the energy is indeed 0. There is no 0-point energy in this system. If it has 0 rotational energy, it means that it is not rotating. Is this a problem though? If you know that it is not rotating, you know where it is. Is that breaking the uncertainty principle? And the answer is no. Although you know it is not rotating, it is not the position that is important, it is the angular position. And its angular position is unknown. It can be anywhere from 0 degrees to infinity degrees. You don't know what angular position it has when it is at rest. The important thing to note with this solution is that for every quantum number j, there is a corresponding wave function and energy level. This is the same as we had for the particle in the box, where for every value of n, there was a corresponding wave function and energy level. The first equation above is in joules. In spectroscopy, we frequently work in units of wave numbers. So how do we convert something in joules into wave numbers? We simply divide through by hc tilde, where c tilde is the speed of light measured in units of centimeters per second. The tilde tells you that it is in units of centimeters and not meters. Anytime I put a tilde above a parameter, it means I am using centimeters and not meters. So if I divide through by hc tilde and I express my h bar as h upon 2 pi, this gives this expression. The energy divided by hc tilde is given the symbol F and is known as the rotational term. I can group the constants together into a constant that is specific for that molecule because it is dependent on the moment of inertia I. We call that constant the rotational constant and we give it the letter B. We use B tilde because it is in units of centimeters to the -1, or reciprocal centimeters, or indeed wave numbers. So it is a derived constant, but it is interesting because it depends on the moment of inertia, and the moment of inertia depends on the reduced mass and the bond length. So if I'm able to determine what the rotational constant is, I'm going to be able to say something about the structure of my diatomic, i.e. what its bond length is. So these are the energy levels of the rotational system that come about by solving the Schrödinger equation. However, spectroscopy doesn't tell me what these energy levels are, because in spectroscopy we're exciting a molecule from one energy level to another energy level. Absorption will occur if the frequency of the radiation matches the difference in energy between the energy levels. So the question is, what is the difference in energy between two energy levels? Will I be able to compare that to the energy in the spectral lines? So let's have a look at the rotational energy levels that come out of this expression. If I substitute for j equals 0 into this expression, my rotational term is equal to 0 wave numbers. If I substitute for j equals 1, I get 2b. If I substitute for j equals 2, I get 6b. For j equals 3, I get 12b. So these are the energies of each of my rotational energy levels. Note that f of j means that f is a function of j. It does not mean that we should multiply f by j. What does increasing j really mean? As we can see, when we increase j, we are increasing the rotational energy. As we increase j, we are witnessing our molecule rotating faster. So that is what is going on at the molecular level. What does j equals 0 mean? When j equals 0, the rotational energy is equal to 0. And yes, indeed, the molecule stops rotating. The other thing that is weird for diatomic molecules is that we only discussed end-over-end rotation. What about rotation about the internuclear axis? Is that possible? Well, let's think about the moment of inertia for that system. If we consider our atoms to be points, which is a good approximation, then clearly the moment of inertia around the internuclear axis is going to be zero, because the atoms lie on the axis and they don't have any size. In reality, of course, the nuclei do have a really small size. And of course, the electrons are not on the internuclear axis. And so the diatomic does have a really small moment of inertia. But remember that the rotational term depends inversely proportional to the moment of inertia. This means that the j equals 1 rotational state that would be at 2b would be at a very large energy. It would thus take a very large energy to excite a transition between any rotational states. For the idealized diatomic of point atoms, the energy required would be infinite. For this reason, we do not consider transitions between energy levels around the internuclear axis. Before we can rationalize all the theory that I've just covered, there is one other thing that I have to discuss, which is selection rules. What are the selection rules of this system? Once more, they come about from consideration of the transition moment. When will the rotational transition moment be non-zero? First of all, the rotational transition moment will only be non-zero if the molecule has a permanent dipole moment. We've already justified that at the beginning of this lecture. Homonuclear diatomics will not interact with an electric field and the electromagnetic radiation. The second selection rule is that when you see a transition, there is a change in the rotational quantum number. That change, delta J, can only be plus or minus 1. It can't be 0, of course, because if delta J was 0, the rotational state would not have changed. We hadn't induced any change in the rotational energy. But why is it plus or minus 1? There is a semi-classical way of appreciating this that has to do with conservation of angular momentum. Remember, J tells us how much angular momentum the system has. The higher the value of J, the more the angular momentum. A photon has 1 unit of angular momentum. The thing is that you don't know if it is plus 1 unit or minus 1 unit. Why would it be plus or minus? Well, you can think of it as clockwise rotation or anti-clockwise rotation. In spectroscopy, we are looking at the interaction of light and matter. In an absorption process, we have a photon being absorbed by a molecule, resulting in a molecule in a higher rotational state. The angular momentum in this process must be conserved. There must be the same amount of angular momentum before the absorption process as there is after the absorption process. Before absorption, our molecule is in state J, and our photon has a unit of angular momentum. Our molecule absorbs that photon. The angular momentum of the molecule can go up to J plus 1 or down to J minus 1. The angular momentum must be conserved. The angular momentum of the photon has been transferred to the molecule. So that is the semi-classical way of looking at it. It is not fully accurate, but it can give an intuitive way of thinking about what is going on. The first selection rule is that the dipole moment, mu, must be non-zero. So if it is 0, we won't see a microwave spectrum, and we call this microwave inactive. Diatomic molecules which do not have a dipole moment are the homonuclear diatomics, such as dinitrogen and dioxygen. Also, of course, symmetrical linear molecules, such as carbon dioxide. Carbon dioxide doesn't have a permanent dipole moment and will not show a microwave spectrum. So any symmetric molecule, such as sulfur hexafluoride and ethene, would also be microwave inactive. How do we know if a molecule is going to be microwave inactive? Symmetry tells us. For these molecules here, the molecules have a centre of inversion. Any molecule with a center inversion will be microwave inactive. We will discuss exactly the nature of the symmetry that has to be present later when I begin our discussion of group theory. So this accounts for our observation 1 and 2. Observation 1 is that a molecule like dioxygen won't have a microwave spectrum, but a molecule like CO, carbon monoxide, would have one. And the reason that it does is because it has a permanent dipole moment. I need to reinforce, however, the fact that just because a molecule is microwave inactive, it doesn't mean that it doesn't have rotational levels. Dioxygen molecules and dinitrogen molecules are rotating just like any other molecules. They have rotational energy levels just like any other molecules. It's just that microwave radiation cannot excite it from one state to another. The way it can change its rotational state is that it will collide with other molecules, and that can change its rotational state. It has rotational levels. The Schrödinger equation will tell us what those levels are, even if we can't see them in spectroscopy. So our selection rule for rotational spectroscopy of diatomics is that delta J is equal to plus or minus 1. This selection rule will enable us to predict the spectrum for a diatomic molecule like carbon monoxide. I know what the energies of the rotational levels are. These energies are given by the rotational term. Because of the selection rule of delta J is equal to plus or minus 1, I can excite the molecule from J equals 0 to J equals 1. Similarly, I can excite the molecule from J equals 1 to J equals 2, again because in this transition delta J is plus 1. I can do it from J equals 2 to J equals 3. But I can't do it from J equals 0 to J equals 2, and I can't do it from J equals 0 to J equals 3. So only certain transitions are going to be allowed. I'll have therefore absorption when I excite the molecule from J equals 0 to J equals 1. I'll also see absorption when I excite the molecule from J equals 1 to J equals 2. I will see a spectral line for every transition from J to J plus 1. I can calculate what the energy is when the molecule is in level J. I can also calculate the energy when it is in level J plus 1. And if I calculate those two energies and take the difference, that difference should be associated with the frequency of each spectral line in my spectrum. So what is the difference in energy between energy levels for which I can excite a transition? What I need to do is write down the energy in the J plus 1 level and subtract the energy when it is in the J level. So using my expression for the rotational term, this is the difference. The rotational term for the J plus 1 level is B times J plus 1 times J plus 2. You get this by substituting J plus 1 into the rotational term expression. The rotational term for the J level is simply B times J plus 1. If I expand this expression, I get the following. And after a little rearrangement, I get the energy difference 2B into J plus 1. So the difference in energy, which is the frequency of the spectral line, will be equal to this expression. So the spectral line for the transition from J equals 0 to J equals 1 will occur at 2B. For J equals 1 to J equals 2 will occur at 4B, and for J equals 2 to J equals 3 it will occur at 6B. The spectral lines, therefore, are going to be 2B apart. They are going to be equally spaced. So this is what the spectrum will look like. The difference between any two peaks is 2B. The lines are equally spaced. Note that the first line associated with the transition from J equals 0 to J equals 1 is at 2B. The second line from the left is that associated with the transition from J equals 1 to J equals 2, and that difference is equal to 4B. So the separation between the first line and the second line is 4B minus 2B, which is 2B. Similarly, the transition from J equals 2 to J equals 3 occurs at 6B. And so the difference between the third line and the second line is 6b minus 4b, which is again 2b. All of these lines are equally spaced. This explains that part of observation 3 that the lines are equally spaced for molecules such as carbon monoxide. We've been able to explain the spectrum of carbon monoxide just by solving the Schrödinger equation. Although this is really quite fascinating, why do it? It is because it is going to give us structural information about the molecule. Remember, our lines are 2b apart. From the spectrum, we can calculate what B is. Remember that B is inversely proportional to the moment of inertia, and the moment of inertia is proportional to the bond length squared. So by taking the rotational spectrum, I am literally measuring the bond length of the molecule. Spectroscopy can give us a great deal of structural information about a molecule. Have a go at this. This is the spectrum I showed earlier, and these are the first few lines of the spectrum, very accurately measured. One thing about rotational spectroscopy, it is very accurate in measuring spectral properties. Calculate 2b, and calculate the bond length for each of the differences. What you're going to see is that the bond length of each of the differences is not the same as you go through these higher and higher rotational states. In fact, the bond length seems to be getting longer and longer. Why is this happening? Well, our assumption that the bond is rigid is not accurate. It can stretch and go through distortion. And as you go to higher and higher rotational levels, the molecule is rotating faster and faster. Not surprisingly, the bond length gets longer and longer. And so that is what is exhibited here by the changes in the rotational constant. This is the end of part 2 of this week's online lecture. Please continue on to part 3.